Okay, so in this video, we're going to look at how to find the limit and how to prove that a number is indeed the limit of an infinite sequence. So if you're unsure about the definition of a limit or what a limit is, then make sure you check out the last video, which I'll link on the screen and below in the description. We're going to look at the example an equals 1 over n. So in this case, we just have a1 is 1, a2 is a half, a3 is a third, a4 is a quarter, and so on. And we want to find the limit as n tends to infinity of this sequence. So let's recall the definition of the limit from the previous video. So we say that a limit as n tends to infinity of an is equal to L if for all epsilon greater than 0, there exists some capital N in the natural numbers such that for all small n greater than or equal to capital N, the absolute value of an minus L is less than epsilon. So we're going to claim that the limit as n tends to infinity of our sequence an, which is 1 over n, is equal to 0. So this is quite an intuitive guess, right? You can see that if you write down the sequence, the numbers are getting smaller and smaller. 1, 1/2, 1/3, 1/4, and so on. You can see that the numbers are getting smaller, so you might predict that the numbers are going to get really, really close to 0. So this is our claim. So the proof is going to be as follows. We need to follow the definition. So we need to let epsilon be greater than 0. So we need to prove this for any epsilon. So we let epsilon be greater than 0. And then in the definition, we need to find some capital N which satisfies the conditions of the definition. So we're going to write choose n such that, and we're going to leave a blank space here where we're going to come back to how to choose n based on what we do later. So continuing and following the definition, we now have that for all n greater than or equal to capital N, an minus L, which is 0 in this case, this is just an, obviously, an absolute value. This is equal to just 1 over n. And because small n is greater than or equal to capital N, we'll have that 1 over small n is less than or equal to 1 over capital N. But now we have a good way to choose n. So we can go back to where we left a blank space, and we can choose capital N to be greater than 1 over epsilon. So in our definition, capital N can depend on epsilon, so this is fine. So if capital N is greater than 1 over epsilon, then we have 1 over capital N is less than epsilon. So we've shown that for all epsilon greater than 0, choose n to be greater than 1 over epsilon, and then an will be less than epsilon for all n greater than or equal to capital N. So we've shown that we can satisfy the definition using these choices. So we have proven indeed that the limit as n tends to infinity of an is equal to 0.